Measurement, analysis, and optimization in semiconductor industry. The semiconductor industry thrives on precision, innovation, and control at the nanoscale. Central to its progress are three interconnected pillars: measurement, analysis, and optimization. Measurement is the foundation. Without accurate, high-resolution measurements of critical dimensions, film thicknesses, and defect densities, process control is impossible. Every nanometer counts, and even the smallest deviation can compromise yield and performance. Analysis comes next. Data must be interpreted intelligently to detect trends, anomalies, or shifts in performance. This enables proactive adjustments and deeper insight into process behavior. Finally, optimization takes the insights gained through analysis and applies them to fine-tune equipment, processes, and recipes. This continuous feedback loop enhances productivity and drives innovation. The phrase "precision at the nanoscale drives innovation" captures this perfectly. In semiconductors, every measurement matters, every analysis informs, and every optimization step pushes the boundaries of technology forward.
The building blocks of modern technology. Semiconductors are foundational to modern electronics. These are materials with electrical conductivity that falls between conductors, like metals, and insulators, like glass. What makes semiconductors unique is that their conductivity can be precisely controlled by adding specific impurities in a process called doping. This adjustability is key to enabling transistors, the essential components in all electronic devices. Semiconductors are at the heart of almost everything in modern life. In smartphones, billions of transistors manage processing, memory, and connectivity. Computers rely on semiconductors for processing power and data storage. In automotive systems, they enable safety, efficiency, and automation in smart vehicles. Solar panels use semiconductors to convert sunlight into clean energy. In medical devices, semiconductors power life-saving diagnostics and treatments. And in lighting, energy-efficient LED lights are possible because of semiconductor materials. These applications highlight the indispensable role semiconductors play in shaping the world around us. Common materials and global impact. Semiconductor technology relies on a range of materials, each with unique properties suited to specific applications. Silicon is the most common semiconductor material due to its abundance, stability, and excellent electrical properties. Germanium played a vital role in the early days of semiconductor development, though it's now mostly used in niche applications. Gallium arsenide is a high-speed material ideal for fast electronic devices and high-frequency applications like satellite communication. Silicon carbide is used in high-power applications due to its thermal stability and efficiency under high voltage. Beyond materials, the semiconductor industry has a massive global impact. In 2022 alone, the market size reached $574 billion. With more than 50 years of innovation, semiconductors have continuously enabled the digital transformation of society, powering everything from mobile devices to space exploration. Their influence is profound and growing every year. Understanding material properties at the microscopic level. Characterization is the science of discovery in the semiconductor industry. It involves systematically measuring and analyzing a material's physical, chemical, and electrical properties. Think of it as taking a detailed fingerprint of a semiconductor device, an essential step in understanding how a material will behave in real-world conditions. The process flow typically begins with preparing a sample, followed by applying measurement techniques, and finally analyzing the resulting data. Key types of characterization include electrical, such as current and voltage behavior; physical, examining size, structure, and defects; thermal, understanding heat dissipation; and optical, studying how materials interact with light. The primary purpose is to verify performance, detect defects, and optimize manufacturing. This matters deeply. Characterization ensures device reliability, improves yield, enables continuous innovation, and reduces production costs. As the industry says, without proper characterization, building semiconductors would be like flying blind: no direction, no control, and no assurance of quality. The science of precision measurement. Metrology is the science of precision measurement, and it plays a critical role in semiconductor manufacturing. It is focused on how to measure, with an emphasis on accuracy, calibration, standards, and uncertainty. Core principles include accuracy, which refers to how close a measurement is to the true value, and precision, which speaks to the repeatability or consistency of results. Traceability ensures that each measurement is linked through a chain to recognize standards, while calibration aligns instruments with reference benchmarks to maintain reliability. It's important to distinguish metrology from characterization. Metrology focuses on how we measure, ensuring consistency, reliability, and comparability. Characterization, on the other hand, emphasizes what we measure, such as the physical, electrical, or chemical properties of materials. Together, these disciplines work hand in hand. Metrology provides the trustworthy foundation for meaningful characterization, ensuring that every piece of data we gather can be trusted to guide decisions in design, production, and innovation. The science of precision measurement. Precision measurement is the backbone of semiconductor manufacturing, ensuring each device meets atomic scale specifications. Key tools include SEM, or scanning electron microscopy, which uses electrons to capture high-resolution images of structures. AFM, or atomic force microscopy, senses forces at the atomic level to map surface profiles with extreme accuracy. XRD, or X-ray diffraction, reveals the internal crystal structure of materials, helping to detect defects and phase changes. Profilometry is used to measure surface topology and roughness with nanometer resolution. These tools cover a wide range of measurement scales, from wafer-level dimensions measured in millimeters down to features in nanometers, and even individual atoms measured in angstroms. Precision matters. Even a 1% measurement error can lead to millions in lost yield. Accurate measurement drives Moore's law, enables advanced node scaling, and supports global compliance with industry standards. The foundation of modern semiconductor manufacturing. Industry standards form the essential backbone of semiconductor manufacturing, ensuring quality, safety, and interoperability across global markets. ISO 9001 is a foundational quality management standard that focuses on consistent process control, continuous improvement, and customer satisfaction. Adhering to ISO 9001 demonstrates a company's commitment to maintaining high-quality manufacturing systems. SEMI standards, developed by the global semiconductor industry, ensure uniform specifications for materials, processes, equipment, and safety. These standards support interoperability and reduce variability between suppliers and manufacturers. NIST traceability links measurements to national standards, ensuring that all precision data is reliable, accurate, and comparable across organizations. Without traceability, metrology loses credibility and value. Importantly, non-compliance with any of these standards may lead to exclusion from global supply chains and markets. Compliance isn't optional. It's a business-critical requirement that drives trust, quality, and access to customers worldwide. The foundation of modern semiconductor manufacturing. Modern semiconductor manufacturing rests on three essential pillars: quality assurance, yield optimization, and enabling innovation. Quality assurance begins with defect detection, ensuring particles or process anomalies are caught early. Process monitoring provides real-time oversight of key parameters, helping avoid drift or variability. Specification validation confirms that finished devices meet tight tolerances, reducing scrap and rework. Yield optimization is a direct outcome of strong control and metrology, or C&M systems. Without C&M, yield may hover around 60%, resulting in costly inefficiencies. With robust C&M, yield can climb to 95%, maximizing profitability and throughput. Finally, measurement and control are also critical innovation enablers. They allow the industry to push the boundaries of Moore's law, from 5 nanometer nodes down to 3 and beyond. Accurate measurements are crucial for developing AI chips, advancing quantum technologies, and supporting the next generation of semiconductor breakthroughs. The foundation of modern semiconductor manufacturing. Investing in metrology and control systems offers exceptional return on investment. A typical ROI is 300%, with a $50 million investment in precision tools often yielding $200 million in annual savings through reduced waste, improved yield, and fewer defects. This means payback can be achieved in as little as 3 to 6 months. Beyond the financials, metrology plays a major role in risk mitigation. Companies can see a 99% reduction in product recalls, a 40% faster time to market, and an 85% drop in customer complaints. These improvements protect both brand reputation and profitability. Most importantly, strong measurement and control give manufacturers a critical competitive edge. Market leaders who invest 5 to 10% of revenue in C&M enjoy faster product launches, higher yields, lower costs, and better quality. These advantages enable leadership in advanced technology markets where precision defines success. Advanced tools for semiconductor analysis. Semiconductor analysis relies on advanced tools designed to extract detailed structural, chemical, and physical data at the nanoscale. Scanning probe methods, such as AFM, STM, and KPFM, offer sub-nanometer vertical resolution, with Z resolution reaching as fine as 0.01 nanometers. These techniques are essential for capturing surface topology and probing material properties at the atomic level. Optical methods, like ellipsometry and interferometry, are ideal for measuring thin film thickness with high precision, down to plus or minus 0.1 angstroms. They also provide insight into optical properties critical for layer uniformity and quality control. X-ray techniques, such as XRD, XPS, and EDS, allow deep structural and compositional analysis, probing up to 100 microns into the material. These methods uncover crystalline orientation and chemical makeup. To ensure accuracy, key success factors include proper sample preparation, well-calibrated instruments, integrating multiple techniques, and relying on expert interpretation to derive actionable insights. Advanced tools for semiconductor analysis. To thoroughly analyze semiconductor materials, engineers rely on advanced tools, each offering distinct advantages across key parameters. The capability matrix compares 4 common techniques: SEM, AFM, XRD, and optical microscopy, across speed, resolution, depth, and cost. SEM, or scanning electron microscopy, delivers medium speed and cost, high resolution, but limited depth. AFM, or atomic force microscopy, offers exceptional resolution and depth, but is slower and more expensive. XRD, or X-ray diffraction, scores high on speed and depth while maintaining moderate cost and resolution. Optical methods are fast and inexpensive, but limited in resolution and depth capabilities. The resolution scale chart places optical methods around 200 nanometers, SEM at 1 nanometer, TM at 0.1 nanometers, and STM pushing atomic scale resolution at 0.01 nanometers. To ensure successful analysis, 4 critical factors are essential: proper sample preparation, instrument calibration, a multi-technique approach, and expert data interpretation. Together, these enable high-confidence insights from macro to atomic scales. Critical hurdles in advanced semiconductor metrology. As semiconductor nodes shrink toward 2 nanometers and beyond, the industry faces a formidable scaling crisis. The path from 22 nanometers to 7 nanometers marked a transition from mature to complex manufacturing. Progressing to 3 nanometers introduced extreme challenges, and now, at 2 nanometers, the industry confronts fundamental physical barriers. At this atomic scale, traditional design and measurement approaches begin to break down, making precise control and characterization incredibly difficult. Key hurdles include quantum tunneling, where electrons unpredictably pass through barriers, disrupting normal transistor behavior. Line edge roughness becomes critical, as even slight inconsistencies along feature edges can significantly impact device performance. Atomic variations in material placement or composition also introduce inconsistencies that reduce yield and reliability. To meet these challenges, metrology systems must achieve exceptional accuracy within plus or minus zero point 0.1 nanometers. Such precision demands highly sophisticated instrumentation and calibration, pushing the boundaries of what's physically measurable in semiconductor fabrication. 3D complexity in advanced semiconductor metrology. As semiconductor devices evolve into three-dimensional architectures, metrology must keep pace with growing structural complexity. Traditional 2D planar designs have given way to advanced architectures like FinFET, 3D NAND, and monolithic integration. These structures now incorporate multiple vertically stacked layers, drastically increasing analysis difficulty. Measuring these compact, multi-layered environments requires tools that can access deep features without compromising resolution. Several hurdles emerge. Buried layers are often physically inaccessible, requiring indirect probing or destructive techniques. Structures can reach aspect ratios as high as 50.1, making them difficult to inspect without distortion or data loss. Multi-stack architectures may include over 100 layers, each needing characterization. Additionally, the interactions between layers add complexity due to variations in electrical, thermal, and mechanical behavior. Compounding this challenge is the use of novel materials, 2D materials like graphene, high-K dielectrics such as HFO2, and quantum-active materials like perovskites, all of which introduce unique metrology demands due to their atomic scale behavior and sensitivity. AI integration and data volume in semiconductor metrology. Advanced semiconductor metrology now requires intelligent systems to handle growing data complexity. AI integration is a key enabler, allowing smart characterization of devices in real time. Through auto-detection, AI systems can rapidly identify defects with higher accuracy than traditional methods. Predictive analysis helps anticipate failure modes and performance shifts before they happen. Real-time process optimization ensures tighter control over variability during manufacturing. Additionally, automated recipe generation shortens development cycles by creating tailored process flows based on live data. This AI-driven shift is necessary due to the sheer volume of data, now exceeding 100 terabytes per day in cutting-edge fabs. This surge is driven by emerging technologies like quantum computing, where coherence measurement is critical. Neuromorphic computing adds complexity by mimicking synaptic behavior, requiring new metrics and inspection methods. Finally, extreme UV lithography at 13.5 nanometers introduces specialized metrology demands. Together, these trends demand scalable AI systems capable of interpreting massive, high-precision datasets, where precision metrology drives innovation. Precision metrology plays a foundational role across diverse high-tech sectors, enabling innovation, reliability, and yield at scale. In the mobile and consumer electronics segment, which includes smartphones, tablets, and wearables, annual production exceeds 2 billion devices. These markets demand extreme power efficiency and performance optimization to deliver long battery life and seamless user experiences. High-precision metrology ensures process control that supports 99.9% manufacturing yield, a critical factor in cost-sensitive high-volume production. In the automotive sector, including ADAS, electric vehicles, and autonomous systems, the reliability bar is exceptionally high. Components are expected to function safely over 25 years. Vision systems and sensor arrays must meet stringent metrology standards to guarantee safety-critical decision-making under all conditions. Any variation could lead to system failure. Meanwhile, data centers, particularly those supporting AI training and cloud computing, face immense thermal and memory challenges. With processors consuming over 300 watts, advanced metrology ensures precise thermal design, memory density control, and performance optimization. In all domains, precision measurement underpins quality, safety, and innovation. Where precision metrology drives innovation. Precision metrology is a key enabler behind the technologies shaping the future, from AI and 5G to the massive expansion of connected devices. In AI and machine learning chips, both for training and inference, compute power is growing at an astonishing rate, about 1,000 times per decade. This explosive growth is powered by advanced GPUs and TPUs, which require increasingly precise measurements during manufacturing to ensure performance and reliability. Meanwhile, IoT and 5G technologies are revolutionizing edge computing and communications. By 2030, an estimated 50 billion devices will be connected worldwide. These devices demand ultra-low power consumption and cutting-edge mmWave technologies to function effectively. Supporting all of this is a massive market, over $600 billion annually in the semiconductor industry. Metrology plays a foundational role in delivering the precision these innovations require to thrive and scale globally. The next decade of semiconductor metrology. As we look ahead, the next decade of semiconductor metrology will be defined by quantum-scale precision, AI-driven automation, and revolutionary materials. In the quantum era, computing technologies from companies like IBM, Google, and IonQ are pushing the boundaries of precision. Quantum systems, such as superconducting qubits and trapped ion platforms, demand measurement accuracy to within plus or minus 0.01 nanometers, orders of magnitude beyond traditional metrology. To meet this challenge, AI integration becomes essential. AI delivers a 10x increase in speed and cuts errors by 50%. It enables real-time defect classification, predictive process control, and automated optimization, making manufacturing more responsive and intelligent. Additionally, novel materials are coming to the forefront. These include graphene-based 2D materials, engineered metamaterials, quantum dots with size-dependent effects, and quantum-active perovskites. Together, these trends will transform semiconductor innovation, and precision metrology will be at the heart of enabling it all. The next decade of semiconductor metrology. The semiconductor industry is rapidly evolving, and the roadmap for metrology innovation over the next decade is both ambitious and transformative. By 2025, advanced EUV lithography will push the limits with sub-2 nanometer nodes. In 2027, AI-first inspection will become a reality, enabling fully autonomous defect detection. Looking ahead to 2030, quantum sensors will deliver atomic-level precision, revolutionizing how we measure and control semiconductor processes. By 2035, molecular assembly will emerge, using bottom-up design to build devices molecule by molecule. Precision in metrology is also evolving, from plus or minus 1 nanometer in 2020 to plus or minus 0.1 nanometers by 2025 and plus or minus 0.01 nanometers by 2030, ultimately reaching atomic-level resolution in 2035. This technological trajectory supports robust market growth. The metrology segment alone is expected to grow to $15 billion by 2030, with a compound annual growth rate of 25%, contributing to a semiconductor market already exceeding $600 billion. The next decade of semiconductor metrology. Key takeaways. Metrology stands at the heart of semiconductor innovation, and its role is only growing more critical. First, it is essential for success. Precision metrology enables yields above 99%, which translates to massive cost savings and operational efficiency across billion-dollar fabs. Second, it is a core innovation driver. As the industry moves towards sub-2 nanometer technology nodes, metrology is the tool that allows engineers to push those boundaries with confidence and accuracy. Third, an AI revolution is reshaping how we measure. Smart systems are transforming traditional measurement paradigms, enabling real-time decisions and closed-loop feedback. Lastly, the quantum future demands atomic-level precision. As quantum computing emerges, metrology must evolve to characterize components at the atomic scale. In summary, the future is precise. Characterization and metrology will remain the invisible yet indispensable foundation enabling all progress in semiconductor technologies.